Thank you. Thank you very much for that warm introduction, and thank you for Royal Society. Delighted to be here, and delighted to be here with our two esteemed guests. So before I sit down and we have a conversation, we want to hear from them. First of all, we'll hear from Dr. Evelyn Keaveney with a short presentation on her research, and then it will be followed by a short presentation by Dr. Guy Paxman. So first up, let's please welcome Dr. Evelyn Keaveney.
Hi guys, thanks for coming. Today, we're using this? There's a microphone. Or this one? I probably move around, so I'll use this one. Can everyone hear me? Yeah. So today I want to talk about carbon on the move, from frozen ground to lakes, water and lake mud. So I'm interested in what happens in the frozen Arctic ground when it starts to thaw. So with climate change happening and Arctic warming up faster than other areas of the world, this is happening already. So it might sound like a story just about dirt, but it's also a story about climate. So you can see this core here. This is a core from Alaska. It's peat that was previously frozen. And afterwards, maybe you can come up and touch it and then go wash your hands. But you can see here, you can see what is happening with the carbon on the move from the core into the lake. And you can see this is what happens when this core was frozen and previously stored carbon. When it gets wet, when it thaws, carbon moves into water, within this water. For purposes of chronology, this is about 1,000 years old. So maybe you've got the Battle of Hastings here. Maybe Henry VIII was getting rid of his wives around here. And we've got tech, COVID, etc. up here. So this is a record of time, but it is also carbon that has been stored for a long time and is now being released. So when the frozen ground does thaw, carbon moves from this frozen soil, which has been stored for a long, long time. Permafrost is carbon, is soil that has remained frozen for a number of years. Sometimes millennia, decades, or hundreds of years. So what happens is when the system warms up, microbes that would have been dormant when frozen start to metabolize carbon. They consume it and they turn it into carbon dioxide and methane. And this is where you hear about the permafrost gaseous emissions. But as you can see, it also goes, the water coming out also has carbon going into it, and that can end up in lakes. And some of it is dissolved in the carbon in the water as tiny particles, much like sugar in tea. So I want to know where this waterborne carbon goes, and this is what my research tracks. So I follow the carbon trail. This is the lake I studied in Alaska. I want to find out whether it goes into the lakes, what happens to it when it is in the lake. Whether it's, I take water samples to actually analyse the carbon that's in the lake right now, moving within the lake system. I take lake sediment from the bottom of the lake, which is mud at the bottom of the lake. And then I also take the permafrost carbon cores so I can see what age they are and whether I can identify that age in the lake. And the way I identify the age is using radiocarbon. Radiocarbon is, I'm sure you've heard about radiocarbon dating before. I don't use it for dating, I use it for identifying carbon sources. But what radiocarbon, every living person in this room has a certain level of radiocarbon. When plants exchange with the atmosphere, they take up radiocarbon that's in the atmosphere. When we eat plants and animals, we then take up that age. So the water in the lake should be modern, but carbon can be offset in different systems. For example, how many of you eat fish? Any freshwater fish people here? Anyone eating inland fish? Yeah? So anyone eating marine fish would probably appear about 400 years older than somebody who doesn't eat any fish, me. If you're in a lake, or if you're eating fish from a river or a lake in a limestone catchment, you could be 1,000 or 2,000 years older than a contemporary area. So if you eat a lot of fish, you can confuse a lot of archaeologists. So what I have looked at initially in my project is to look at the water that's in the lake and look at the carbon that's in the water in the lake. And I have shown, using radiocarbon, that there's different ages to the carbon that's in the lake. I've analysed it with radiocarbon, and I have seen that different radiocarbon analysis done at different temperatures has shown different ages of carbon. So this suggests that dissolved organic carbon that is floating in the lake, like your sugar in the tea, is actually derived from permafrost. The lake water that I picked up last September is about 2,000 years old. So this must be previously frozen permafrost carbon that has come out in the water. And you don't really need to understand that graph fully. It just shows that the carbon that's in the water is a mixture of young and old carbon and evidence of permafrost carbon moving. So where does this where does this carbon go? It can go into the sediment, and I will be looking at some sediment to see if I can identify that permafrost signal in the sediment. And if it is in the sediment, then it could be restored. It could be buried again in that sediment and layered up, and it's not an issue for emissions. However, in the lake, there are critters, there are animals, there are invertebrates, there are microbes that would be consuming this carbon, turning it into CO2. If the lake becomes saturated in CO2, it basically belches out carbon dioxide or methane. Again, greenhouse gases. So that could also be an outcome. Or it could be transported down sea. The water is on the move, the carbon will be on the move. It can go downriver and downstream and end up in the ocean, where again, it could be buried or metabolized into CO2. So basically, I found that a lake can store carbon, release carbon, or carry carbon onwards. At the moment, I don't know which, but I can definitely tell you that permafrost carbon is on the move.
Thank you.
I forgot to say about the core. This core is from Alaska, and if anyone wants to touch it later on, they can.
Okay, thank you very much. So we will obviously have lots of questions, fascinating. So let's move straight to Guy Paxman, for your presentation. Thank you.
Hi folks, great to see you all. So yeah, my name's Guy. I'm a polar scientist up at Durham University in the northeast of England. So what I'm going to try and do in the next 4 or 5 minutes is to give you a really quick whistle-stop tour of the hidden world beneath the Antarctic ice sheet. Okay, so sort of switched hemispheres from Evelyn's talk. And hopefully I'll give you a sense of kind of what we're doing and why it's quite interesting, and why it matters as well, why it's important. So I want to introduce you first of all to this idea that there are two Antarcticas, really. So there's the Antarctica that you probably will have in your imagination. So you're from the sort of tales of Scott and Shackleton, sort of evocative early 20th century sort of stories. You might have seen it in documentaries of Frozen Planet, or you might have even been fortunate enough to have visited that area. And really it's that icy, remote wilderness. Not a lot there, a lot of ice, icebergs, a few penguins. That's kind of about it, okay? And actually, in contrast to the Arctic, Evelyn's sort of focusing on, you might have seen in the picture, she had a map where the Arctic is basically a frozen ocean surrounded by land masses, okay? But at the South Pole, we have an ice sheet which sits on a land mass. We've got a solid continent underneath the ice sheet, okay? And that ice sheet has been there for a long time. So the Antarctic ice sheet is about 34 million years old. It's by far and away the longest lived piece of ice we have on Earth. Okay? And it's doing a really, really good job of hiding what's underneath. So more than 99% of Antarctica is covered by ice today. Okay? So the second Antarctica really is that hidden landscape underneath. And it is really well hidden. So in places, the ice is as thick as 4.8 kilometers, okay? So in old money, it's about 3 miles from top to bottom. It's so deep that the parts of the landscape below that are further down from the surface than the Titanic shipwreck is from the surface of the Atlantic. That's kind of the scale that we're dealing with the Antarctic ice sheet, okay? And it's not going to happen today, so don't worry, but if that were to be removed, that ice sheet, we could raise sea levels around the world by 60 meters, okay? That's not going to happen anytime soon. Just to give you a sense of the vast scale we're talking about. So how do we actually know what's underneath the ice sheet? So I've got a little video to explain that. Now, the eagle-eyed amongst you will realise this is not Antarctica, this is Greenland. But to give you an example, so essentially we use aircraft to survey what's underneath the ice sheet. And these aircraft fly across the top of the ice, and they're using a technique called radar surveying. Okay, so the aircraft are emitting radio waves, radar waves, which travel through the ice. They bounce back off the land at the bottom, and they return to the aircraft. Okay, so we see an echo of those radar signals coming back to the aircraft. It takes a fraction of a second for it to go all the way down and back, but because we know the velocity of the radar in ice very precisely, we can calculate the distance that the radio waves have traveled. It's just speed multiplied by the time it takes, the time delay. Okay? And from that, we can work out the thickness of the ice sheet and therefore how high the land is at the bottom. Okay? And that's kind of, as a sort of polar scientist, Antarctic and geophysicist, this is what we're surveying. So we are now building up quite a good picture of what the landscape looks like underneath the Antarctic ice sheet. Okay? And hopefully you can get a sense from the image there of the scale that we're dealing with. You can see Britain and Ireland on there for scale. But also the kind of the variety of terrain that you can see, hopefully, in that sort of rendering. You can see high kind of mountainous regions in the sort of dark brown and tan colours. Okay, and you can see the sort of lower-lying, flatter basin areas in the blue colours. Okay, so there's a real variety. Antarctica is actually an incredibly diverse range of landscapes underneath the ice sheet, much more so than in some other parts of Earth's continents. Okay. So my research really focuses on thinking about what can we learn from this landscape? What does it tell us about the history of Antarctica, going right back to before the ice existed, through the history of glaciation, and then what that tells us about how the ice sheet is behaving today and how it will change in the future. So I want to finish by giving you just a couple of what I think are quite interesting examples of landscapes underneath the ice sheet. So we see vast hidden mountain ranges under the ice sheet. Okay, so here's a mountain range which is as big as the Alps, it's as wide and as high as the Alps. It's called the Gambutsev mountain range, and it's completely hidden by the ice sheet. There is no outcrop of this mountain range. It's entirely hidden. Okay? We think this is where the ice sheet first began to grow in Antarctica. It's one of the highest places of the continent where the early kind of ice caps, glaciers would have first been forming, and then they grew out from there. Okay? So this landscape is almost a landscape that's kind of frozen in time. It's beneath a very stable part of the ice sheet today, almost cryogenically frozen in place, protected from erosion, all the usual processes that happen at Earth's surface. And it's basically a completely sort of relic landscape of a former world in the sort of very early stages of Antarctic glaciation. Finally, another example, not all places are like that. Some places have been much more heavily modified by the ice sheet. This is an example of a subglacial trench, the Denman Trench, which a number of which sort of cut across the edges of Antarctica. And now the Denman Trench is actually the deepest place anywhere on any continent on Earth. Okay? So we can't actually see the bottom of it. It's so deep and the ice is so thick. But we think it's around about 3,500 meters below sea level. Okay? So just for reference, the Dead Sea is at about 400 or so meters below sea level. That's how vast this feature is. You could stack the tallest building in the world in there more than 4 times. It's huge. Carved out by glaciers, glacial erosion over millions of years, essentially. And these trenches kind of form the arteries that allow the ice sheet to drain from the center to the coast and for it to sort of flow to the sea. And they obviously therefore govern how fast that happens and how responsive the ice sheet is to changes in temperature, changes in air and ocean temperatures. Just a couple of examples there, but hopefully you can see how we sort of can use the clues in the landscape to build an understanding of how the ice sheet behaves, and we can maybe chat a bit more about that in the discussion. So I'll leave it there for now. Thank you very much.
Okay. Thank you very much. They were both fascinating talks, mini talks about you give us a real insight into your research. And I know that some of you will have questions already, and I just want you hopefully to just keep those with you, keep yours in your head. We're definitely going to make time in the session for questions from the audience. But before we do, I've got 1 or 2 things I'd like to ask myself. First of all, they're quite, I'd say, specialist areas of research, and it'd be nice if you maybe just spent a little while just giving me an insight into, let's say, if you were a youngster, and how did you get into this particular area of research? What was your trajectory? We'll start with yourself, Evelyn.
Well, I guess I've had a pretty lucky, maybe. Well, I've worked hard, but my trajectory, basically, I did science in school. I loved biology, my favourite subject. I scored highest in biology in my Leaving Cert, which is the equivalent to A levels in the UK. I went to Trinity College in Dublin and I did zoology. And then I went from zoology to York to do zooarchaeology and got more into the past history. And then I went to Queen's in Belfast to do radiocarbon dating. So I've had a very odd trajectory. I haven't just stayed in the same field of research, but I think the fact that my background is different from other people working in paleoecology or carbon cycling research, I can bring my insight from zoology and from ecology. So I would say, do what you love. I guess specialise in what you love, but talk to other people as well. Talk to your lecturers, talk to your teachers about what would suit you the best as well.
Excellent. So you'd say a large part of it was following your passion to some extent and
Absolutely.
sort of building on that.
And then following what my research went as well. Which way?
Absolutely. Okay, Guy, what about yourself?
Yeah, I guess the romantic sort of story would probably be, sort of hearing about the sort of stories, and I mentioned it briefly there, the sort of stories of kind of Shackleton expeditions and sort of the kind of ridiculous stories of kind of get shipwrecked in the sea ice and having to row hundreds of miles to sort of find kind of salvation and rescue, if you like, and that sort of maybe kind of captures the imagination in some ways. But I never really thought about it much at that stage. That was just a bit of sort of like a romantic ideal. But I guess it kind of ultimately, similar in a way, through school I think I was very indecisive at school. I liked quite a few different subjects. I was quite into sort of most science, kind of chemistry, physics and maths and physical geography as well. And when it came to sort of thinking about what to do at university, I was really sort of stuck what to choose. And I think got some very good advice, which is basically, have you thought about kind of earth sciences, something like geology, where you can actually combine kind of all of those things into something that's kind of applying all those kind of different interesting areas of science to kind of solve problems to do with how the Earth works. And that's kind of what really sort of chimed with me as something that I thought would be really interesting. And then the sort of polar science kind of thing just sort of followed from there again, a bit accidentally. I just sort of got into it by chance through sort of, different kind of things that I read and worked on during my undergraduate, and then kind of, went from there really.
Okay, well, thanks for that. So now let's get into some of the sort of science. I mean, in a way, you've already started to allude to my next question, which is about the interdisciplinary nature of your research. It is quite interdisciplinary. It covers all sorts of different areas like ecology, geology, chemistry, even atmospheric physics, all sorts of areas. So do you consider yourself as a sort of interdisciplinary scientist, or do you consider yourself more as a specialist who helps to sort of contribute to a sort of broader picture? Let's start with yourself, Evelyn.
I would definitely think I'm an interdisciplinary, I may not be able to pronounce it, but interdisciplinary scientist. I think using radiocarbon, most people would know that it's for radiocarbon dating, for doing chronology associated with archaeology, but I don't use it for chronology, I use it as a biomarker, so I can tell where my carbon in my lake is coming from. Other ecologists use radiocarbon to look at food web studies. So if they're looking at fish conservation, they can look at the age of the fish. They can also look at food web stuff to see if the fish are feeding on older carbon in the lake or not. And that has come from my research. And I've already told you about the archaeology of bones and how you could all confuse archaeologists in the future with radiocarbon things. So I have worked in all those sorts of areas, and I think...
Excellent.
And I would like to also say I hated maths in school. That's not a deal breaker for science.
Okay. What about now? Okay, we'll leave that one. You don't have to answer that one. It wasn't one of my official list of questions. Guy, yourself, are you a specialist or are you more interdisciplinary?
Yeah, I think probably I would echo a lot of what Evelyn just said there. I think I would definitely consider myself to be relatively sort of discipline hopping. I kind of like to sort of bounce around a bit, and I think in some ways with polar science it's perhaps often quite necessary to do that, because we're often dealing with quite sparse observations, quite limited amounts of understanding, so being able to kind of draw on methods from different fields, so whether it's more sort of physics, whether it's more geology, whether it's kind of climate science, I think they all kind of come together to answer the same sort of questions that we're all very interested in. I think, that being said, there is a necessity, I think, to work across teams, whether it's within the UK or internationally, where there is different expertise. So I guess with the radar surveying that I was talking about, ultimately we need the kind of engineers and the physicists to be able to design and implement that technology. If you ask me to build a radar system, no way. But if you ask me to then interpret what the radar system images and what it shows using kind of methods from geomorphology, from geology, that's a bit sort of more up my street. So that's kind of a combination that we kind of tend to use. It's a bit of both.
Excellent, great. So I think the general message is sort of work hard at all your subjects if you're at school, just to keep your options nice and open. So let's talk a little bit more about your actual research, because you've both done research at the poles, albeit potentially different ones, but there's a lot of talk about the poles melting and so on. So what are the consequences of the poles melting, and also is it actually reversible? It's open to either of you to maybe give it a go.
I guess I can go first again. Well, from the Arctic, the poles melting, a lot of the ice in the Arctic is sea ice. So yes, it's cold frozen ice, but it's not going to add as much to the sea level as land ice. So if land ice does melt, it can go into the sea, raising sea level, as you spoke of. My research has shown that the permafrost water will also melt. And then that is because of warming, obviously. But the additional thing is that the Arctic is currently a very unproductive system. It's asleep almost. The stuff is laid down very, very, very slowly. So this core here is a very, very long record because it has been laid down so slowly. Peat bogs in Ireland, for example, are more thick because they're more productive. So when I say productive, plants are growing, animals are living, and microbes are awake. So the emissions from microbes can add to this this warming as well. So when I say can it be reversible, maybe in thousands of years with the natural cycles of the Earth, yes. We could maybe slow things down at the moment. So honestly, I'm not sure how reversible it is. I think it's more a chance of lobbying your politicians to try and minimise whatever heating is happening at the moment.
Okay, and same question to Guy.
Yeah, so I guess the view from the Antarctic is a little bit different. So we are talking much more about land ice in the Antarctic, as I mentioned. So the sea level implications of melting in Antarctica are significant. As I mentioned, it's a 60 meters worth of ice locked up there. It looks like there's no way that's getting lost anytime soon. But you can imagine with an ice sheet of that scale, even 5% of that ice sheet is a significant amount of meltwater. Okay, and you can imagine the implications that would have sort of socioeconomically for coastal communities in particular. I guess other implications as well for Antarctica. We're talking about an area that's really at the center of kind of global climate and ocean circulation. So the production of kind of cold, dense water in the Antarctic really drives a lot of the kind of ocean currents and circulation that you see. So if things start to change in Antarctica, you'd expect that then has far-reaching implications. It knocks on to circulation patterns and the implications, for example, on weather patterns around the world, on fish stocks, agriculture, all these things. It's hard to predict exactly how that will change, but if things keep going the way they're going, that will change. Okay.
And again, is it reversible?
I think the reversibility question is one we're really kind of thinking a lot about in Antarctic science. There's this idea of sort of tipping points existing or points where you get this sort of domino effect where once you reach a certain level of warming, it kind of cascades a sort of series of kind of things that drive further kind of melting and ice mass loss. We still don't know exactly kind of where those tipping points exist, and I expect the answer is they apply to certain parts of the ice sheet and not to others. So in places we might think warming and the consequence of warming can be reversed, but in other places that potentially is not the case. So that's something to be, I think, very careful about.
Okay, right, so don't forget to keep those questions in the audience. I will be opening it up shortly, but I've got a few what I'll call relatively quick-fire questions. One specifically to Evelyn. How does carbon actually get trapped in the permafrost in the first place? I mean, you've talked about carbon being trapped, and I just wondered what's the mechanism for trapping carbon specifically?
Well, it's basically that stuff dies.
Right.
So you've got plants, animals, everything moving around, living, etc. When they die, they go into the soil, they decompose, and that happens over time, and layer upon layer upon layer upon layer of dead material stacks up, becomes, it decays, it's acted on by bacteria, but it just basically makes a record like this where it's just laid down and laid down and laid down. And that happens at the bottom of the sea, the bottom of lakes, and in soil and in peat.
Okay, so quick question for Guy. The land surface of Antarctica is said to have been mapped at a lower resolution than Mars, apparently. So that means we know more about Mars than Antarctica. So the question is, why is this? Is this just because of the ice, or is it difficulty getting there? Well, Mars is pretty difficult to get to, so, but why is that?
It's a good question. Yes, they are both very difficult to get to. The main reason that Mars is much better mapped, and the Moon as well, for example, is the technique we can use to basically use lasers to kind of measure how high the surface of those planetary bodies are. And that can be done on satellites, which is very expensive, but it's quite efficient, and they can do that kind of quite efficiently and quickly in constant orbit. The problem and actually we can do that to map the surface of the Antarctic ice sheet really in very good detail indeed. But the problem is that those lasers, they can't see through the ice, so we have to rely on the radar technology, which is, at the moment, we don't have the capability to put that on satellites from that distance away from Earth and get the sort of the right sort of signal. So we have to do it the more old school way with aircraft, which is just much more time consuming. And also they're limited to a very narrow window in the year when you have light and weather that's kind of hospitable enough to be able to go and do that surveying.
Okay, sorry, just to push that a little bit, but a manned mission or personed mission to Antarctica, would that be more feasible than to Mars?
Do you mean just to sort of get people visiting?
Well, I mean, if you needed to go there to actually take more data, why wouldn't we just naturally think about just going there? I mean, I know we can have remote sensing and so on. Just a thought.
Good idea. I think part of that comes down to sort of the logistical side of things as well, and the logistical challenges that are involved, and also just getting enough research funding to be able to go and do it as well.
Okay, fair enough. So that's another cue. Maybe the Royal Society and others can think about, giving you an idea for a project proposal. Okay, so we're nearly ready for questions from the audience. I'll have one last one maybe to Evelyn. So how does the Arctic compare? I know we know that if the poles were to melt, would there be anything more sort of than just the sea? Would there be anything more what would happen within the sea apart from obviously more carbon, I suppose, in there?
Well, yeah, sea level change can happen with, say, things like the Greenland ice sheet. If that melts, that would be the same as the Antarctic ice sheet melting. So that would produce or put a lot more water into the sea and increasing sea level. And as Guy said, there's a lot of ecology in the sea that would be disrupted. You may have sharks moving to different areas and have more shark attacks around the UK and Ireland. You'll have stuff following phytoplankton, all the algae and all the little invertebrates that move to different areas. If that cold water enters the sea, that's going to change all of that sort of ecosystem, which changes the carbon pump as all those things die and fall to the ground. So there's an awful lot of intricate systems that we don't all fully know about.
And I'm putting on my slight sci-fi head. Could it produce new species and things we've never seen before and that sort of thing, bringing back species that existed hundreds of thousands of years ago? It's just a thought.
I don't know.
Who knows?
There's probably species in your dark, deep trench that we don't know about.
Exactly. Yeah. Okay, I think I've done enough questioning for now, but I'd be really delighted to hear from the audience on questions about any aspect of what's been discussed today, both the presentations and the subsequent Q&A. So, any questions from the audience? Yep, one up front here.
Thank you. So this one's for Evelyn. So you mentioned you're not sure what's going to happen with the carbon that goes into the lakes after melting from the permafrost. Do you kind of have an idea about how you're going to approach finding that out?
Yeah, well, when I was in Alaska, I took the water samples, and that's what I have analysed first because basically they go off quicker. So my sediment is currently frozen, but I will do the same sort of analyses using radiocarbon down a core that will cover about 200 years, which is the period of rapid climate change. So I'll be able to tell, say, if I have old carbon coming into the lake and more old carbon coming into the lake at the top, that shows that permafrost is contributing more to the top than the bottom. So say there'd be a natural state where the permafrost is frozen, the carbon is locked away, then what I'm dating should be the actual age. If permafrost comes in and I date that and it's older than what the actual age is, then I know it's permafrost. I don't know if I've explained that well.
Yeah, thanks.
Okay, great. Any other questions? Yep.
That's handy. It was for Evelyn. Now, I think I've read that radiocarbon dating is not very reliable for very recent dates since 1945 because of nuclear weapons having been used and tested. But it sounds encouragingly as though you can.
Yeah, actually, when the nuclear testing was happening, that put loads more radiocarbon into the air. So there's something called a bomb peak. So there's natural levels of radiocarbon. And then there's this bomb peak around 1945 to 1955. And it has steadily dropped. The good thing is, though, that they identified radiocarbon right at that time. Therefore, they took monthly samples of the atmosphere over that time. So you can actually date to the year, to the month. In some areas for that, it's called hot radiocarbon. Our lab doesn't work on hot radiocarbon.
No.
Because if we had something that had radiocarbon levels up here, it would confuse the machines when I'm trying to date something down here. Other labs do. And it is also coupled with CO2 levels. They also use it to, the same labs capture the CO2 levels. So any time you hear we're going over 400 parts per million, it's mostly radiocarbon labs that are doing that. And then they date it to see what the age of the atmosphere is.
Thank you.
Fossil fuels, though, are making it reduce again. So that's another question.
Something slightly positive about.
Okay, we've got a question. Okay, we'll take the one here and then we'll go at the back there, or back there. Yeah.
Thank you. Yeah, this is one for Guy. Maybe a slightly sci-fi-ish question, I'm not sure. So underneath the ice on Antarctica, do we think that the ice is pressed hard against the ground everywhere? Or are there places where actually there might be space beneath the ice? You know, is it sort of, are there potentially sort of air pockets under there? And like, what might that look like?
So is it all uniform density or is it different?
That is a good question. I think it's definitely possible that you could get localized areas where you could have sort of, if not sort of full air pockets, then maybe like icy cavities almost within the ice. We certainly know there's liquid water down there. The ice is pressing down so hard that the melting point of the ice at the bottom is significantly below zero under pressure. So actually quite a lot of the Antarctic ice sheet bed, because it's also being fed by the geothermal heat from the ground, is actually above freezing. So it's quite a lot of liquid water exists at the base of the ice. There are huge subglacial lakes underneath the ice sheet, and we think also quite dynamic in places, kind of channels of water. So it's possible that within that you could have areas where there is also no water and no ice, and sort of localized air pockets and that sort of thing. So, but I don't know if we have a way of kind of actually surveying that. Water is very easy to find because it kind of shows up very clearly in the radar sounding, but air, unless it was a very substantially large pocket, would probably be very hard to spot. So I don't think we know the answer to that for sure. Good question.
Okay. I think there was a question here from the lady over there. Yeah.
Thank you for the exciting stories. I'm just wondering, what's the most exciting expedition each one of you have been on?
Okay, good question.
Well, I guess I went to Alaska last year. I went to a scientific station. If you saw the pictures at the very, very start of my slides, they were aurora borealis that I took myself, got up at 3 o'clock in the morning, and they were spectacular. The scientific station was in a very, very, very remote area. I don't know if any of you have seen ice road truckers. The Dalton Highway runs from the top of Alaska to the bottom of Alaska to Fairbanks. My scientific station was 4 hours from civilization in one direction and 10 hours in the other direction. To get 3 flights and a 4.5 hour journey or drive to get to my site. Once I was there, the food was fantastic. They had a chef on site. He did Taco Tuesdays. He did Italian Wednesdays. He even had an Irish night for me. Not sure how Irish the food was, but so no, it was really, really brilliant when I was there. I would also say Alaska kind of looks like Ireland. It kind of looks like the Midlands of Ireland, except that the mountains are far away instead of small. But yeah, it was pretty exciting being there.
Excellent. Guy, it's hard, tough act to follow, right?
It is, yeah, especially because I'm about to drop the big confession of the tour, which is I've actually never been to Antarctica.
Fair enough.
But I have fortunately been to Greenland a couple of times for field work, and I think my obvious answer to your question is that. And I think being able to sort of fly across the ice sheet and just sort of get a sense firsthand for the scale involved, and seeing kind of all those features that you kind of read about in the textbooks in real life was stunning, and just the sort of the sense of the scale there as well, the vastness and the vast emptiness, I think was kind of what you take away probably most, and also sort of how warm and welcoming the people were as well who live in Greenland. So yeah, fantastic trip. Yeah.
Excellent. One of the hidden benefits of being a scientist, which they don't tell you about. When you do those global types of topics, you can go to some really exotic places, nice places. Excellent. Do we have a final question from the audience? Oh, here we go. One here.
Since fisheries need colder water, as ice sheets melt, could we end up seeing less fish despite there being more water?
Interesting question. Okay. Anyone?
I could answer that. I could give a sort of stab at answering that from an Antarctic perspective. That's an really important question in the Antarctic because the Southern Ocean is a particularly rich area for marine life and fish stocks, and it's a big kind of industry and sort of way in which resources are exploited in the Southern Ocean. There's definitely a concern about warming ocean temperatures there. So even as you say, there's more water going in, but temperatures become warmer. That can be a problem for a lot of those species, and particularly in the Southern Ocean, a lot of species have evolved over millions of years to be very specially adapted to cold water. And as the water's warm, they haven't got the ability to adapt that fast enough. And the problem is they can't swim further south because there's a continent in the way, so they can only go so far. And we're already seeing kind of krill and other species, their distributions starting to shift around a bit and become a bit more unpredictable because of the change in temperatures. So yeah, definitely something that is a challenge in the Southern Ocean for sure.
Okay, and Evelyn, I know you don't eat fish, but is there anything you could add to this?
I guess just repeating the same thing as well. There's going to be differences in the fish or the animals that can evolve more quickly and have a little bit of more plasticity or a little bit of less of a niche diet. Because some species just feed on one thing, whereas other species can feed on lots of different things, and they may be better to survive more easily than the ones that are very, very specialised. But there's definitely going to be changes in ranges of some fish, and some fish won't survive. Some may flourish.
And obviously changes in salinity and potentially pH levels and so on. And it really brings home how delicately balanced the ecosystem is and how it's all interconnected. So if anything else, that's certainly brought that home for myself. Is there any other question? I know I said the final one, but we might have time for one more. If not, I'd like us to put our hands together for our key contributors, Evelyn Keaveney and Guy. And I think that brings this session to a conclusion. So thank you for your attendance. I hope you enjoyed it, and enjoy the rest of your time here. Thank you.